بسم الله الرحمن الرحيم وبه نستعين والصلاة والسلام على أشرف المرسلين. السلام عليكم ورحمة الله. We are going to start our webinar series today with introduction to material properties and time-dependent behavior to set the floor for the coming talks and trying to unveil the confusion when using the frequent terms to describe material properties. Here are some case scenarios that can be used during your vivas. For instance, the examiner might ask you, draw the stress-strain curve, label all the points, axes and nomenclature, and describe what the areas underneath signify. By the end of this talk, you will be able to describe the stress-strain curve. You will be able to describe the attributes of viscoelastic material and to explain the SN curve, or what is known as the fatigue curve, the endurance limit, and the difference between fatigue limit and fatigue strength. Now let's start with basic definitions. What is biomechanics? Biomechanics is the science that deals with forces acting on living bodies, whether external or internal forces acting on living bodies. What is biomaterials? Biomaterials is any substance or combination of substances, synthetic or natural in origin, which can be used for any period of time as a whole or as a part of a system, which treats, augments, or replaces any tissue or organ or function of the body. There are frequent terms that we use in our practice, like force, load, stress, and strain. So what is force? From physics, force is the action that causes acceleration of a mass in a certain direction. And we use during our practice a synonym for force is the load. Load is actually a force acting on a living body. What is the value of force? It's Newton, which is equal to the mass kilogram times the acceleration, mass times meter per second square. And the value of force is Newton again. So what is stress? So what is stress? Stress is force applied to a material per unit area. And again, we use the terms force, load, and stress interchangeably or as synonyms. The force unit is Newton. And when we try to quantify this force, or trying to be more objective, we use the word stress. It is force per unit area. When the force is applied to a material, it can be a compressive force, tensile, bending, or shear force. So what is strain? When a material is subjected to a force, strain is the change in shape or the deformation that occurs to the material. It is usually a percentage or a proportion, and it is calculated by the change in length or height over the original length or height. The materials that we frequently use in our practice can behave differently according to the direction of force, and it can be divided into two types. Either isotropic materials that behave identically irrespective of the direction of the applied force, and the example for such materials, metals and alloys. On the other hand, we have anisotropic materials like our cortical bone that behaves differently according to the direction of force. And as you can see here, that our bone can withstand high compressive forces and it will not fail before sustaining more than 200 newtons per meter square if the force was a compressive force. But when we are exposed to a tensile force, the bone will fail at a lower stress, less than 150 newtons per meter square, and we are weakest to shear forces. The bone will break or will fail at stresses lower than 100 Newton per meter square. So the term anisotropic means that the bone behaves differently according to the direction of force. Our bone can withstand high compressive forces, and it is weakest to shear forces or torsional forces. In order to describe the different materials that we use in our practice, we need to understand the basic terms of material behavior exhibited on the stress-strain curve. The stress-strain curve used by the physicists to compare between different materials, and it's the product of stress and strain. We have on the x-axis the strain, which is the change in the shape of the material to a given force or stress. The physicist will expose the material to different forces and will draw the curve. As you can see, at the beginning it's kind of linear and then it becomes curved. I will try to explain the different regions and points on the curve. As you can see here, we have what is known as the elastic region. Try to imagine that you have a rubber band in your hand and you start to stretch this rubber band. At the beginning, once you remove the stretching force, the rubber band will regain its original shape. It will regain its original shape. And that is when the material in the elastic region. Once you remove the force, it will regain its original shape. This will continue to a point known as the yield point, which is the transition between the elastic and plastic deformation. At a point when you stretch this rubber band, once you remove the stretching force, you will observe that this rubber band didn't regain its original shape. Why? Because we have a plastic deformation, or what is known as permanent deformation of the material. Why do we have this phenomenon? That once we removed the force, it didn't regain its original shape, because at the microstructure, the fibrils or the molecules or the grains or the crystals start to experience tears or breakages. That's why we have a permanent deformation in the material. Increasing the force will increase the deformation and the change in the material till we reach to a failure point where the material will eventually fail, or we will have a gross breakage in the material. Let's dive into more details which can make your life difficult during the viva. The examiner might ask you about the yield point, which is the transition between the elastic and the plastic region. The yield point is actually made of 3 points: the proportionality limit, the PL, and the PL. The line under the PL, or the proportionality limit, is linear, so it follows the Hooke's law, and you will have predictable strain to a given stress or force, while the line between the proportionality limit and the elastic limit is not linear anymore, so it doesn't follow the Hooke's law, but the material is still exhibit elastic properties which means if you remove the force, the material will regain its original shape. Now, between the elastic limit and the yield stress, or what is known as the yield stress, you need the amount of force that will produce 0.2% of deformation. So, in the yield stress, it's actually the amount of force required to produce 0.2% of permanent deformation. Now, if you are comparing different materials in the elastic region, you are allowed to use certain terms. As you can see here, we are comparing between different materials in the elastic region. Okay? We have materials from 1 to 11. As you can see, material 1 is ceramic, material 2 is alloys, 3 stainless steel, 4 titanium, and 5 is cortical bone. Okay? Usually in the elastic region, we have the curve is kind of linear. That's why it follows the Hooke's law. When a material is loaded in the elastic zone, the stress is proportional to the strain. It's predictable because it's a linear line. It follows the Hooke's law. So to compare between the different materials in the elastic region, you want to find out which material is stiffer or less flexible. Those are the allowed terms when you are describing a material or you are comparing between two materials in the elastic region. You can describe the material as material A is stiffer than material B, or material B is flexible or more flexible than material A. Okay, and to be objective, we use what is known as the Young's modulus of elasticity to quantify the stiffness of the material. So, what is the Young's modulus of elasticity? We have here three materials. Material A, the red one, material B is the green one, and material C is the purple one. Now, as you can see, with respect to material A, we need a higher stress to create a smaller deformation in the material, while the same stress, if we applied it to material B, the green one, we will have a larger deformation. That means material A is stiffer than material B, or material A is the stiffest material in this stress strain curve, while material C, the purple one, is the most flexible material when compared to material B and material A. The Young's modulus is the gradient or the slope. It is the stress over the strain. And whenever we have a numerator-denominator relationship, if the denominator is small, the denominator, which is the strain, small, it means we will have a higher Young's modulus of elasticity. So the materials which have a high Young's modulus of elasticity, it means this material is a stiff material, while materials which have small Young's modulus of elasticity, it means the material is flexible material. Why? Because it is a relation between the numerator, which is the stress, over the denominator, which is the strain. Here the stress is larger than the strain, as you can see here. So we will have a high Young's modulus of elasticity, while when we look at the purple line here, the stress is smaller than, which is the numerator, smaller than the strain, the denominator. So we have small Young's modulus of elasticity, which means the material is flexible, requires small amount of force to create a larger shape deformation. Again, when we compare between different materials, we say that ceramic is stiffer than cortical bone. Curve 1 is the stiffest material. Line number 11, which is cartilage, is the most flexible material on the graph. So based on the stress strain curve, comparing different materials in the elastic region, ceramic is the stiffest material, titanium is the closest material to cortical bone, polymethyl mesacrylate is between the cortical and cancellous bone, and cartilage is the most flexible material in this graph. So how can we apply the previous knowledge to our practice? Well, in trauma setting, we usually use intramedullary nails, and the material of the intramedullary nails, the most frequently used is titanium or stainless steel. It's better to use titanium intramedullary nails because its Young's modulus of elasticity is closer to the cortical bone, so it is a better load sharing device than using stainless steel. Why? Because of the stress shielding phenomena. The closer the material Young's modulus of elasticity to the cortical bone, it will share loads with the surrounding bone, and the bone will remodel and will remain healthy. But if the material is very stiff, like using an extensively porous coated stem, the forces will be transmitted to the lower edge of the stem, and then from there to the cortical bone at the distal part of the stem. The proximal part of the femur will not experience any forces, and it will lose its density according to the Wolff's law. Our bone will adapt according to the loads or forces that falls on the bone. If there is no forces, it will lose its density with time. That's why it is better to use proximal coated stems, because the forces will be transmitted more proximal to the cortical bone, so it's a better load sharing device, and it will keep the bone healthy, and the bone will have a good density with time. Now, with respect to the plastic region, the material can be described either as ductile material or brittle material. Ductile material will undergo large amount of deformation before it fills. On the other hand, brittle materials will undergo a small amount of deformation or no deformation before it fills. An example for a ductile material, like the metals, stainless steel, titanium. On the other hand, a brittle material like ceramic, which will undergo a small or a little or no deformation after the elastic region before it fills or it sheds. Well, in the viva, the examiner might parts of the plastic region. We have yielding, strain hardening, and necking. Once the yield point is passed, the material will undergo considerable elongation or yielding with little or no increase in the stress. This is known as yielding. And then we have strain hardening. This is where the plastic deformation increases a material resistance to further deformation. It occurs due to the material undergoing changes in its atomic and crystalline structure. And this is where the grains in metal dislocate and slip, paradoxically increasing the resistance to further strain. Okay, reaching to the ultimate stress. So what is the ultimate stress? The ultimate stress is the maximum stress that the material can sustain before fracture. And as you can see from here, the curve will start to move downwards to the fracture point. And we have here what is known as the necking. So after the ultimate stress point, stretching occurs with an actual reduction in the stress. Why? Because we have necking or wasting in the material, where we have the cross-sectional area is reduced, and it will reduce till we have a gross failure in the material. So as you can see here, if we are comparing these two materials, if somebody asks you which material is stronger, you will say material A, which is the brittle material, is stronger than material B, which is the ductile material. Why? Because material A has got a higher ultimate tensile strength. But if the examiner asks you which material is the toughest material, actually material B is tougher than material A. Why? Because it has got a larger area under the curve when compared to material A. That's why sometimes the terms are confusing. When we ask which material is stronger, we are actually looking at the ultimate tensile strength of the material. If the material has got a higher ultimate tensile strength when compared to other material, it is said it's stronger, which is a bit naive. So now we have a different curves and we would like to compare between them. Curve A, it has got high strength, the highest ultimate tensile strength, that's why it has a high strength, but it's brittle. Why? Because the material has a smaller deformation before failure, while material B has a larger deformation before failure. That's why it's ductile material. And material B is tougher than material A because the area under the curve for material B is larger than the area under the curve for material A. The same. If I ask you to compare between material B, the red one, and material D, the blue one, material A has got high strength and this is low strength. Material A is a brittle material that undergoes small amount of deformation before failure. Material D is a ductile material that undergoes large amount of deformation before failure. Now, if I ask you which of the following has got which of the following is the toughest material, I think you are going to choose the material that has got the green curve. It's a ductile material and there is a large area under the curve. So material C is the toughest material in this stress strain curve or stress strain graph. Now, with respect to tendon and ligaments, when you want to describe the stress strain curve, I want you to pay attention to what is known as the toe region. It is a non-linear elastic phase initially traveled under minimal stress as the crumpled fibers straighten out. Why? As you can see, the fibers will be crumpled. You need to straighten the fibers before it follows the linear part of the elastic region that follows the Hooke's law. So with respect to tendon and ligaments, remember, if the examiner asks you to draw the stress strain curve for a ligament or a tendon, you have to draw the toe region. It is a non-linear elastic phase. It occurs initially till the crumpled fibers straighten out, and then it will become linear, or it becomes. Now let's move to viscoelastic materials. What is a viscoelastic material? It is a material that exhibits time or rate dependent stress strain behavior, and the behavior of the material will depend on the load magnitude and rate at which the load is applied. Viscoelastic materials has got 4 attributes: creep, stress relaxation, time dependent strain behavior, and hysteresis. Creep, the first attribute of a viscoelastic material. It is time-dependent deformation in response to a constant load. If you have a string or a rubber band and you hang a weight to its distal end, you will have an initial length. Then if you come after 5 hours and you measure the length, you will find that there is an increase in the length or deformation of this string or rubber band. This is what is known as time-dependent deformation in response to a constant load. Where do we apply creep in our practice? When you do the Ponseti method or serial casting to correct patients with talipes equina varus. Stress relaxation, the second attribute of a viscoelastic material. It is time-dependent decrease in load required to maintain a material at a constant strain. The best example to describe this is when we rasp the femoral canal while we are preparing our femoral canal in total hip arthroplasty. We use the rasper, we hammer on it, we wait for some time for the stress to come down, because if you keep on hammering the rasper, the stress will go up and the bone will shatter. So you need to wait for some time for the stress to come down, because our cortical bone is a viscoelastic material to accommodate the shape of the rasper, and then you move to a larger size. With respect to time-dependent strain behavior, the rate of change of length of the material affects the behavior? Well, the faster the strain rate, the higher the stress at a given level of strain. Let's have a look on the following X-rays. The one on the left shows a classic nightstick ulnar fracture. The one on the right is showing highly comminuted fracture of the humerus, reflecting that the patient has sustained high energy trauma. And the kinetic energy is equal to half times the mass times the velocity square. So the main determinant of the kinetic energy is the velocity of the incriminating object. For the X-ray on the left side, or the simple fracture of the ulna, it is due to a stick held in the hand of somebody and he hit the victim. On the right side, we have a missile injury. There is a huge difference in the velocity when we use our hands and when we use a pistol or a K-19 rifle or DHK, or what is known in Sudan as Doshka. The mass of the bullet is the mass of the bullet when you use a pistol. It is smaller than Kalashnikov or K-19, and the Kalashnikov or the K-19 bullet is smaller than the one of the DHK or the Doshka, and the velocity is totally different. As the velocity increases, this missile injury or the bullet will hit the bone and it will transfer a large amount of energy in fraction of a second, and the bone will act as if it is a stiff material, while when we apply the energy at a lower rate, the bone will act as a flexible material. That's why we have on the left image a simple fracture, and on the right side we have a highly comminuted fracture. Now, with respect to hysteresis, it refers to stress-strain curve differing during loading and unloading. The amount of force or stress required to change the shape of the material during the loading phase is larger than the one in the unloading phase. And why did that happen? Because we have changes in the microstructure of the material, and strain energy is lost in the form of heat between loading and unloading. Okay. Now we are going to discuss the fatigue curve. Some of the questions that might appear in your Viva is: what is the SN curve? What does it mean? And please label the axis. They might ask you, please relate the fatigue curve to both total hip and total knee replacement. What are the things that we need to know about the fatigue curve or the SN curve? The SN curve represents the material's performance under cyclical loads. It plots the number of cycles, the stress magnitude or the log of the stress on the y-axis against the number of cycles in millions on the x-axis. Materials fall into two categories, both based on whether or not they have a fatigue limit. Still, we will have a curve, a gentle curve with a plateau and at the region where the curve plateaus, we have what is known as the endurance limit. So what is the endurance limit? Is defined as the stress at which the material can withstand 10 million cycles without experiencing fatigue failure. And that's an arbitrary number used by the companies that manufacture orthopedic implants. They claim that the material can withstand 10 million cycles before it fails. And the material can, on annual basis, can withstand 1 million cycle. So at least the material that you are using can stay without failure for 10 years. Now, the fatigue limit. If the stress amplitude is reduced below a particular threshold, which means if the material sustains a stress that is lower than the endurance limit, fatigue failure will not occur for an infinite number of cycles. Theoretically speaking, if the material sustains a stress below the endurance limit, it can withstand infinite number of cycles. But for most of the materials, that is not true. We have no fatigue limit, which means fatigue failure will eventually occur irrespective of the stress amplitude level, what is known as fatigue failure, which is failure of the material due to repetitive cyclical loss below the ultimate tensile strength. Now, in this graph, we are comparing between two different materials, this steel and aluminum. The steel has got endurance limit, while the aluminum have no endurance limit. The steel curve has a gentle plateau, while the aluminum curve will continue to go down till the material fails or have gross failure. That's why it has got no endurance limit. This is known as fatigue limit, and this is known as fatigue failure, showing two different behaviors for different materials. So how can we apply the knowledge that we have from this SN curve in our practice? Well, if the examiner asks you which type of polyethylene are you going to choose in total hip arthroplasty or in total knee arthroplasty, your answer will depend on your understanding to the SN curve and to the biomechanics in total hip and total knee. In total hip, the metal head will have high contact area with the polyethylene insert. So this high contact area means that the stress is distributed over a large surface area, so you have a low contact stress. So when it comes to polyethylene, you will choose the polyethylene that has got better wear properties, which is the highly cross-linked polyethylene. On the other hand, when it comes to total knee, you know that the condyle of the knee has got a low contact area with the polyethylene insert that looks like a dish. So you have a high contact stress, which means that if they ask you which type of polyethylene you will choose in case of total knee, you will go for the polyethylene manufactured with better fatigue properties, which is the ultra high molecular weight polyethylene, which is fatigue resistant, while here you are going to use the highly cross-linked polyethylene, which is wear resistant. has got a better wear properties. Let's have a look at fatigue properties of bone. Bone has interesting fatigue properties. In vitro experiments show that bone does not have a fatigue limit and is susceptible to fatigue failure at even small stress amplitudes, given an adequate numbers of cycles. In vivo, bone, however, has the capacity to repair, and any fatigue-related microdamage stimulates bone remodeling. Fatigue failure of bone only occurs when the rate of microdamage exceeds the rate of remodeling, as we can see in stress fractures like the metatarsal fractures in the soldier recruits. Let's recap and see what we have learned so far. With respect to the elastic region, you are allowed to use the following terms: flexible and stiff. You can say that material A is stiffer than material B, or material B is more flexible than material A. In the plastic region, you can use the following terms: ductile and brittle. Ductile if the material undergoes large deformation before failure. With respect to the ultimate tensile strength, if you have a material A that has a higher ultimate tensile strength when compared to material B, you can say that material A is stronger than material B. If we are comparing two materials, one that has got a large area under the curve compared to material B which has got a small area under the curve, we say that material A is more tough or tougher than material B. Bone can be described as anisotropic and viscoelastic. Anisotropic because it behaves differently according to the direction of force. We can resist compressive forces better than shear or torsional forces. The bone is viscoelastic because it shows time or rate dependent stress strain behavior. With respect to the SN curve, we knew that some materials have endurance limits like the steel, and some other materials they don't have or they don't exhibit an endurance limit like aluminum. Thank you very much, and now the floor is open for questions.